Can everyone hear me? Okay, so hello everyone. My talk is dedicated to the automatic means of topic labeling. Okay, as we all know, topic modeling describes a corpus in terms of latent topics in it, and we get the thing here is that a topic is usually represented as a list of top words that got the highest probability. And this is why the task of automatic topic labeling appears, because especially if we have a large number of topics, in order to understand what they are all about, we have to look through all of the words and draw some conclusion. This is not very convenient, and the goal of our task is to find a concise and meaningful label that would describe content of the topics. And as with many other tasks, the problem has been studied for English, and there are a number of methods how to do it, but not all of them are applicable to Russian, and this field is still actively developing for the Russian language. Firstly, I'm going to describe an algorithm that we use as a strong baseline method in our research. We take first k topic words for each topic and pose it as a single query to a search engine. Then we collect the titles of the top n search results and pre-process them, concatenate into one continuous string, and feed it into the text rank algorithm. Text rank, it was firstly introduced for the English language, but it was proved to be consistent for the Russian as well. It firstly transforms the text into an oriented graph, and where nodes represent lemmas and edges, and their weights are defined by some similarity metric, for example, the co-occurrence of the words within the input text. And next, the text rank value is computed for each node based on in and out degrees of this node. And as a result, we get this text rank value, its weight for each word. But in order to use not only single tokens, but n-grams as well, we worked out a set of morphological patterns that extract grammatically valid key phrases. And phrase's weight is computed as a sum of weights of its constituents. So as a result of this procedure, we get a set of candidate labels with their weights. Before describing our proposed algorithm, let me explain how explicit semantic analysis works. It was firstly introduced by Gabrylovich and Markovich in 2007, and it was tailored to capture semantic relatedness of texts. It is based on Wikipedia, and on the basis of Wikipedia, an index is created where words that occur in Wikipedia articles are represented as vectors, and figures in these vectors are TF, IDF values that stand for the association strength between this word and Wikipedia articles. And when we have a text, we can find in this inverted index vectors for each word in the text, and using the weighted sum, obtain one vector for the whole text. And once we have a vector representing the text, we can, for example, compute the cosine value between the vectors and to get a relatedness value. As for our approach, as I've said, ESA gives us a vector in the space of Wikipedia articles, and we can sort this vector in the descending order, so that we get a list of articles titles that describe the given input the best, that are the most relevant for the input. And in our approach, we make use of the described graph algorithm, except that instead of a search engine, we use explicit semantic analysis. And then titles that are got from ESA are processed in the same way as search engine results on the previous step. But before doing, our study is based on a corpus of Russian encyclopedic text on linguistics, and we obtained 20 topics from LDA, Latin Direct Allocation, and each topic was represented by 10 words, top 10 words, and they served as inputs for ESA and for the Yandex search engine. And 30 most relevant results, both from ESA and Yandex, were processed as I have described. They were concatenated and given to the text rank, and a set of weighted labels was obtained. But before doing so for ESA, we examined articles' titles yielded by ESA and decided to edit them by excluding some of them. First of all, the articles that are dedicated to people, because people's names are not likely to make a meaningful topic label. Also containing numbers, because numbers are not supposed to serve as a topic label. Words not in Russian as well, because we work with Russian texts, and so it's not supposed that not Russian text would be considered a label. And also very small articles, because there, for example, could be some articles dedicated to alphabet letters and so on. And most importantly, titles with the mark disambiguation, because such titles refer to pages that link with links to some other pages, and they do not contain meaningful information. Also, in course of our experiments, we noticed some peculiarities, some characteristic features of ESA, and when it is given topic words as an input. First of all, some results seem to characterize only a few topics words out of 10. For example, if a topic contained a word dialect, the first articles that ESA yielded describe mostly different kinds of dialects. So this is connected with the way how ESA processes, how it computes the vector for the text, because it gets vectors for each word, and if some word contains very high TF-IDF values, in the resultant vector, they tend to outweigh all other TF-IDF values for other words. Also, ESA finds hyponyms more likely than hypernyms, and this is because in specific articles, words we are trying to characterize are normally mentioned more often than in general articles, and so they get into the results. But for topic labeling, hypernyms are more likely required. So we need, for a word like glasny or vowel, we would need articles like sounds and phonetics, and not high front vowel. And finally, ESA does not take homonymy and polysemy into account, because words in the dump of Wikipedia are not provided with such information, and as a result, some articles in the output may be connected with different domains. So, okay. We worked out a set of rules that actually turned out to improve the performance of our algorithm. Okay, maybe it would be more convenient to look at straight at the examples. If a two-word label is a part of a longer label, so we make it shorter to get from statistical machine translation just machine translation. Also, we exclude very long labels because they're often too specific. And we try to deal with cases, like I mentioned, where so that, for example, we have lots of different dialects as candidate labels. We just replace it with the word dialects. Here are other examples for two topics. There are top 3 labels by ESA-based algorithm and by Yandex-based algorithm. Maybe we can return to this slide later, and now let me talk about the evaluation. Well, there is a problem with evaluating topic labels, but we decided to make use of experts and manual evaluation, and experts were given 10 words per topic and 2 labels, one from the labels ESA approach and the other one from labels Yandex approach. And we asked them to assess which of the 2 matches the topic better, and it was also possible to mark both or none as relevant. And here are some evaluation examples. There is a topic, 2 labels, and pluses and minuses that how our experts evaluated them. We also computed mean value for the methods, considering pluses as 1s and minuses as 0s. And here are the results: 0.47 for labels ESA and 0.54 for labels Yandex. It is also there is a number of moments worth mentioning about the approach based on the Yandex search engine. First of all, when trying to automatically obtain search results from a search engine, we can see that there are often limitations on the number of queries, for example, per second from one IP address, which really slows the processing of, slows all process and makes it takes more time than ESA. And also, search engines often use complex algorithms of ranking, and what's more, the results are often individualized for a specific user, so that results of the method on this algorithm cannot be reproduced. And so we claim that labels ESA works comparably to labels Yandex, and it has a number of advantages, as I said. So its runtime is not dependent on external factors, and it is based on a certain Wikipedia dump, so that the results provided by this algorithm are consistent. And so we conclude that our approach is a reasonable alternative that also exploits some advantages. Thank you for your attention.
We have 2 minutes for questions. We will ask some questions for this talk. Questions, that's interesting because work is impressive and ESA is something that's special in terms of corpus processing. So I have a question about the applications of this technique, because you're using an approach to infer topics, and you infer topics from different data sources. And what is the benefit of ESA with other approaches and how to apply it?
We use ESA to label topics, right? The idea is that there are not so many methods to do it for the Russian language, and we studied we explored the approach, the one that we use as a baseline, and compared it to ESA, and the results are, as I said, that ESA has some advantages that that method lacks, and that's the...
More questions? Well, I see no raised hands. Thank you again.
Okay, thank you.